So we want to take a look at the effect that lenses have on observing an image. I've got a picture here, and I've got a lens which is not a glass lens, it's not a plastic lens. It is a water lens, we'll call it. And notice the effect of my water lens. Notice the effect that the water lens has on the image. So we have a radically different image. There's my scorpion. Notice the effect of the water lens on the light rays that are reflecting off of that picture. And yes, what you see when the lights are turned on, you see the light rays that are reflecting or bouncing off of those images and entering your eye, or in this case, entering the camera lens, another lens, and then your eye. So, one more time. Now notice, if we move this closer, let's see if this changes. Notice we're getting some magnification now as we move the lens closer to the object. Now notice we have magnification, but also interesting, really interesting, we don't have a reversal of the image anymore, or reversal of the, there's my scorpion. And as we move back, so as I move the lens closer to the object, away from the observer, or further away from the object, closer to the observer, notice we have a big difference in the effect of the lens on the light rays that are bouncing off of that. Again, there's my scorpion. So really interesting, complicated, interesting, and you can see figuring this stuff out could lead to a nice job as an optometrist, where you would be fitting different people for glasses. And it's all about understanding how lenses work with the light rays to produce an image. So here's my water lens, but now I want to have my water be the object, and here's my simple microscope. Simple microscopes have one lens, so notice. One lens, and we're getting a magnification here. A compound microscope has two lenses, and how these work is interesting and important in terms of physics, biology, astronomy, optometry. So there's a huge number of applications here. Let's go back here, and notice I'm getting nice magnification. Let's add a little bit, so let's add a little bit of this pebble and then magnify it and see if we can look at the effect of this chemical reaction. Okay, and then we'll magnify. So now it's magnified. Somewhat, not great. Right, so here's a picture of my t-shirt, which has one of the greatest bands of all time. I'll introduce them in a moment. But let's see the effect of this picture as seen after the image is reflected off of a plane mirror. So plane mirrors are flat mirrors. Look at how the image has been altered. The light rays, when they reflect off of a plane mirror, are obviously going to be altered. And I did want to, and that's part of this section that we're going to be doing. We're going to be studying plane mirrors. We're going to be studying convex, concave mirrors. We're also going to be studying thin lenses, which allow light to pass through. So these would be lenses for a magnifying glass, lenses for a light microscope. So a wide variety of applications here. And by the way, I want to introduce the members of the band.
Hello everybody out there. My name is John. I want to thank you, John, for allowing me to talk here. This is my friend Paul. This is George, and this is Ringo. And if you're 16 or 17 years old and you don't know about us, you really are missing out. Get it together out there, y'all.
Well, thank you, John, for that. Hello, everybody. This is Mr. Walters, and I'm here with John, Paul, George, and Ringo, as you saw earlier. And it's Sunday, so I'm a little bit more informal compared to what I'd be dressed like on a Monday, Tuesday, or Wednesday. So we've been talking about light, analyzing light, and we talked about how astronomers can determine the composition of the sun and the stars based on the emission spectrum that are produced by the different elements when they are energized. And those line spectra can be thought of as fingerprints and can be read as fingerprints to determine the specific components or elements that make up the different stars, galaxies, and our sun. Just a quick review here. Notice the visible spectrum is red, orange, yellow, green, blue, indigo, and violet. And by the way, I hate to tell you this, but indigo is kind of a made-up color. Newton, who analyzed white light and talked about the components of the different colors that compose white light, he loved 7. He thought 7 was a number that he equated, and others, with divinity. So he added that because he liked 7. Anyway, that's besides the point. So notice, again, that's the visible spectrum. If you go over to the right here, you're gonna have cell phone waves, you're gonna have radio, etc. If you go over to the left, you have UV light, and then you get more high energy wavelengths, X-rays, gamma rays, etc. Notice what distinguishes these different colors from each other, and what distinguishes infrared radiation from UV. One of the defining characteristics, quantitatively speaking, is the wavelength. So notice the red wavelengths over on this side of the visible spectrum, the wavelengths for red are longer, and we're going to use lambda. There's my lambda. That is going to define our wavelength. So there's lambda. Notice that the wavelength is getting smaller as we're going from the red to the violet and then into the ultraviolet, and of course again you'd have X-rays, gamma rays, which we have already talked about with nuclear reactions. Those are high energy. Anyway, as these, just to review here, as these wavelengths get smaller and smaller and smaller and smaller, the energy content goes up and up and up. And the smaller the wavelength, the more punch that those photons are going to have. These longer wavelengths are going to have less and less energy content associated with them. So as we see, the energy content is related to the wavelength. What else is related to the wavelength? We also have frequency. As the wavelength gets longer and longer and longer, the frequency gets less and less and less. They are inversely related to one another. So we have these long wavelengths, low frequency, low energy content. The shorter the wavelength, the higher the energy content, and also the higher the frequency. Frequency is symbolized with nu. So we've got Greek symbol lambda here for wavelength, and then this is nu. But this is frequency, and that's the number of cycles that pass a given point per second. So again, near the end of the year, it's review. It's review. We're going to be talking how light behaves when it passes through lenses. We're going to be talking about reflection and refraction and plenty more. But now I want to make sure we're getting some things down that we've done in the past. Okay? So here is the energy content of a single photon. That tiny little packet of energy. That tiny packet of energy could be for red light, could be for green light, could be for blue light, or it could be high energy ultraviolet light. Again, notice how the wavelength of red versus green versus blue changes. And of course, when that wavelength changes, we also know what's going to happen with the energy content and the frequency. Back to the equation. So here's the energy of a photon, single photon. And notice it's directly related to the frequency. So obviously as frequency goes up, energy goes up. This is Planck's constant. So Planck's constant is going to be used to determine the energy content of a photon when the frequency is used. Again, so that's not going to be changing. Planck's constant, symbolized with an H, is 6.63 times 10 to the negative 34th. Well, what do we predict is going to be the units for Planck's constant? So the units. Obviously a very small number, but remember this is for a single photon, which is minuscule. It's smaller than minuscule. Here is our Planck's constant. What are going to be the units for Planck constant based on this equation? Also, to state the obvious, notice that frequency, as frequency goes up, the energy of the photon goes up. So this mathematically expresses that direct relationship between frequency and energy. Well, Planck's constant, again, small number, but what are the units here? What are the units for Planck's constant? In order to figure that out, we need to look at the units for frequency. Frequency is given as cycles per second, and that is the unit, the name for that unit is hertz. So we could have a kilohertz, we could have megahertz. So 1 hertz versus a kilohertz versus a megahertz. A megahertz would have 1,000,000 hertz. Kilo would be 1,000 hertz. Okay, or you could have microhertz, which are 1,000,000 times smaller than a hertz. Anyway, let's take a look here. We want to know the units. We want to write the units for Planck's constant. So since this is cycles per second, I know that I've got seconds in the denominator. So there I have 1 over seconds, or the inverse of seconds. So that is cycles per second. We're not going to write the cycles, that's implied. Well, energy is going to be in joules, so the units for this are going to be joules times seconds. So let me write that over here. So this is joules times seconds. And notice when joules times seconds, notice there's my frequency. That's the units for frequency. Cycles per second, inverse of seconds. Notice that cancels, and sure enough, we're left with joules as our final unit of energy. The next thing we want to look at is the relationship between the speed of light and wavelength here, and also frequency. Notice the speed of light is a constant, and the value is extremely high. We're traveling this fast, 3.00 times 10 to the 8th meters in 1 second. It's phenomenal. That's approximately 186,000 miles per second. But that number is a constant, and that's important. And Einstein realized how important that was. And that universal, that number remains constant, was really important in determining his theory of general relativity and also special relativity, especially special relativity. General relativity showed us that light was affected by a gravitational field, which is amazing, and it changed the concept of how gravity works. You've got Newton's law of gravity, which mathematically is perfect. It's great. It put a man on the moon. But even Newton admitted that he defined gravity mathematically, but he freely admitted how gravity worked. What actually was causing gravity was a complete and utter mystery. Of course, Einstein talks about gravitational fields, large gravitational fields, warping space and time. And when that space and time is warped, and if it's warped significantly, and I mean really significantly, you can end up with black holes. Anyway, let's get back to here. So notice, commit this to memory, commit this to memory. Let's relate the energy of the photon to the wavelength now. So let's mathematically combine these and come up with a way to look at wavelength and relate it to the energy content of the single photon. So here's our energy of the photon. There's the speed of light. Here's Planck's constant. Again, Planck's constant is this value, 6.63 times 10 to the negative 34th. Notice that's in joules times seconds. Of course, when this value is times by frequency, seconds, frequency is the inverse of seconds, again, duh, and we'll cancel that out and we'll leave, our answer is going to be in joules then. But notice we can relate it now to the wavelength. So now, if we know the energy of the photon, these are two constants, we can mathematically rearrange this and get the wavelength and then fit in that wavelength to known values. Notice 700 nanometers here. Sorry, it's over there. 700 nanometers red light, 400 nanometers violet. If we know the wavelength, we can fit in the, we can figure out where in the electromagnetic spectrum we are. Of course, if we're a shorter wavelength than 400 nanometers, 400's violet, then we're moving into ultraviolet, and if we're getting shorter and shorter, we're moving into these really high energy short wavelengths like X-rays and of course the gamma rays. Here's what I want you to do. We have a photon which has the frequency of this. So here's our frequency in hertz. This photon is traveling ultra fast, and we're going at 7.5 times 10 to the 14th cycles per second. So picture this in your mind, picture a given point and picture wavelengths passing that given point at that high value. Of course, hertz is the inverse of seconds. So what you need to do now is tell me the energy content associated with that and tell me the wavelength that is associated with that frequency. Have at it. Got it? Energy content and wavelength for that photon. Here is my given frequency in hertz. That's cycles per second, units, inverse of cycles. Notice I want to plug into my energy equation here. So energy equals Planck's constant times frequency. So here's my Planck's constant, h. Here's my frequency. Notice my units, I've got joules times seconds, so let's cancel that, and I'm left with joules. Let's do the math. So let's do the math. Plug this in correctly, please. And notice that's going to be my energy, but it's important to realize that's the energy, very, very small, but that's per one photon. So I'm just going to write in here per photon to remind us that certainly it's small, but don't get that confused. One atom has this tiny, tiny, tiny amount of mass, like a gold atom, whatever, 1 times 10 to the negative 23rd grams. Right around in there, close enough. That's one atom. But when you have a mole of gold, the number goes up to macroscopic, where you can measure that mole of gold. So that would be 197 grams if you had a mole of those atoms. What's a mole? 6.02 times 10 to the 23rd. So take a look here. Before we get to the next answer, let's convert this from joules per photon, convert it to joules per mole, and then give me that answer in kilojoules. Okay, do that. So here's my energy in joules per 1 photon. So notice set up and cancel, factor label, problem solving. So important. Physics, chemistry, biology, any sort of engineering. It's all about problem solving. And by the way, you have to move freely from the metric system, English, and back just by doing simple conversions. You have to be able to do that. So you got to be able to convert joules to kilojoules, to megajoules, to microjoules, and back again. Well, anyway, notice we just want to set it up properly to where it cancels, to where you're left with the units that are desired. What I told you to do was to convert this small number of joules per photon into kJs per mole. So we're going to move from joules per photon to kJs per mole of photons. Notice, I know that there's 6.02 times 10 to the 23rd photons in 1 mole. Notice, there and there, canceled. Now, if I stopped right here, I've got the joules in a mole of photons. Well, let's go from joules per mole to kilojoules per mole. So notice here, I've got joules up here high. What's the relationship between joules and kilojoules? Let's see. Is it 1 joule in 1,000 kilojoules? Is that a valid conversion? 1 joule per 1,000 kilojoules? No, that doesn't make any sense. It's the opposite of that. In 1 kJ, there's 1,000 joules. So let's use that. We've got 1,000 joules per 1 kJ. And notice that cancels, and we're going to be left with this number. Let me plug it in. We're going to be left with 299 kJs per mole of photons. So that's the energy content of a mole of these individual photons. This is meaningful in terms of in a lab sort of situation. This is not as meaningful, but it's important because you need the energy per photon to get to the kJs per mole of photons. And that would be mole of photons as opposed to moles of atom of gold. Well, let's get back to our example here. We know that this is the energy per photon. Notice here, let's focus on this equation. I have this value that I just determined. So we'll put an X here. I know this value, it's a constant. I know this value, it's a constant. Planck's constant. I don't know that, but any time you have one equation and one unknown, you can solve algebraically. If you have 3 equations and 3 unknowns, you can solve it algebraically. So let's plug in what we know here. So here we go. There's my energy per photon. So that's my E value, then C H lambda. Let's rearrange algebraically. And we get to here. So notice wavelength. This is wavelength equals C times H divided by the energy content per photon. look at canceling here. Seconds and seconds cancels. Joules and joules obviously cancels. Our answer is going to come out in meters. Let's come up with the answer in meters, and then we're going to convert it to nanometers. So let's do that. 4.00 times 10 to the negative 7th meters. There's my wavelength, very, very small, but my frequency is very, very, very high, so you'd expect with those small, small wavelengths, higher and higher frequency. So now, convert that to nanometers. And then, once we know the nanometers, we can fit it in our visible spectrum or see where it is relative to the wavelengths in the visible spectrum. Notice 700 to 400 nanometers, nm. Let's convert meters to nanometers. What is it? In 1 meter, there's 10 to the 9th nanometers, or is it for every 1 nanometer, there's 10 to the 9th meters? Well, obviously a meter here, 39 inches approximately, that's a meter. There are a billion nanometers per 1 meter. So you take that meter stick and you divide it a billion times, and then you can use that relationship for a conversion. Meters cancels. We're going to be left with 400 nm. So 400 nanometers, and notice that puts us at the far end of the visible spectrum. So 400 nanometers, so they're violet light. If the wavelengths are smaller and smaller and smaller, that throws you into UV light. Watch out. Damages your retina, damages your skin. It is linked to skin cancer. Okay? All right, you're going to try one more. Now we're going to start with a wavelength, and I want you to determine the energy content associated with it. So let's go with, instead of violet light, let's go deep into the UV spectrum. So we have UV, and let's go with 90.0 nanometers, and we want to determine the energy content associated with that. Have at it. I'm given ultraviolet light with the wavelength in nanometers. So this is 90 nanometers. Again, a frame of reference is 700 nanometers to 400 nanometers is visible light going from red to violet. So there's my lambda. I want to figure out the energy content associated with that. Here are 3 formulas. It's always helpful to write the formula. Maybe you know for sure what it's going to be, but if you're unsure, you write several. It's going to be one of them, most likely. And if you can't figure that out, you need to study more. But notice, we're looking for energy. So there's energy also, but let's use this. And let's see what we're given here. We're given only the wavelength in nanometers. So I've got, I'm going to put an X there because I'm given that. We want to find this, so let's just put a little question mark. Take a look. Speed of light is a constant, so we know that. We're given that. There it is. And that's Planck's constant. And Planck's constant would have to be given and that is 6.63 times 10 to the negative 34th joules per second. Well, there you go. Notice I can solve for this easily. Freshman year algebra, right here. So look at what I've done. I'm doing a little plugging and chugging right now. So I've got speed of light, I've got Planck's constant, I've got my value here in nanometers. Notice canceling seconds and seconds cancels. Let's see here. This is in meters. This is nanometers. What do we need to convert that? You're darn tootin', as they say in Fargo, North Dakota. You're darn tootin'. You need to convert that. Let's get this to meters. What's the relationship between a nano? Nano's really, really small. Nanometers and a meter. So it's going to be 10 to the 9th, or 1 times 10 to the 9th. Nanometers are in 1 meter. So 1 times 10 to the 9th nanometers per 1 meter. Notice, cancel, cancel. Now meters is on top, meters is down low here. I'm going to come out with an answer in joules, and it looks like I'm going to get this after I plug in. That's the, I plugged in after I chugged. The chug is the calculator here. 2.21 times 10 to the negative 18th joules. And again, that's joules per 1 photon. All right, that's not bad. Could I have done this another way? I could have. Here's my UV in nanometers. There's my wavelength. So let's go over to this formula. I know wavelength is given, so I can put an X. Speed of light's a constant, so I'm always going to be given that. And then notice I can solve for frequency. When you solve for frequency, it would look like this. The algebra would look like this. So now frequency equals speed of light divided by lambda. Beware, beware, beware. Nanometers here. Speed of light is in meters. Again, that you got to convert. Let's get the nanometers to meters. Once I get this correct answer, then I could plug it into here and get my energy of a single photon. So notice I solved here. Now I can put an X here. I can put an X here. There's my question mark, and notice I can get the energy. I'm seeing a relationship here. I'm looking at this. I'm looking at these two, especially this algebraic derivation of this. So notice, if I substitute in this for frequency, let me get rid of this. So notice, frequency equals C over lambda and that was easy. Notice earlier I said this is an algebraic combination of these two, and that's how that's done. CH, HC, same thing, and then lambda. All right, I'm going to give you practice problems. I want you to get conversions down. I want you to get problem solving down. I don't want you to leave this class without getting comfortable with that. Then we're going to be talking refraction, reflection, more about light. And we're going to be talking again, plane mirrors, convex mirrors, concave mirrors, convex lenses, so a lens versus a mirror, big difference between the two, One allows the light rays to pass through, the other one doesn't. That's the game plan. All right then. Have a good day, and I will post practice problem solving. And it's going to include conversions within the metric system and around the metric system, etc. Because I know you honors physics people, not everybody has gotten that down yet. Or at least gotten it down to the point where it needs to be just wrote and just can be done quite easily, and it's one less thing to worry about. This is essential if you're interested in being an engineer. It's essential if you're interested in studying any of the mathematical sciences, which include chemistry, physics, and others as well. So I'll post homework. Get that stuff done. Have a good day.